Yo, I'll kick this off. So yes, welcome to the Minibems breakfast briefing. And in these strange times, yeah, we thought it would be good to start communicating via this method. Just to reiterate, yeah, if you've got questions, we want this series to certainly encourage questions and debate. But on this occasion, if you could just write your questions down, and we'll either Alistair will either pick them up during the presentation or respond to them at the end. Yeah, so first off, just for those of you who may need a bit of reminding, what is Minibems? Minibems provides a heat network performance service. Our suite of managed services include, firstly, heat network optimization software that controls flow rates in real time. Secondly, we leverage our Internet of Things-based, data-driven approach to provide heating and hot water triage using real-time remote diagnostics. Third, we offer comprehensive metering and billing services with both prepayment and credit billing systems available. The goal is to provide heat network performance. We are trying to make systems more efficient, reducing primary fuel costs, reduce carbon emissions, and improving reliability and reducing unplanned maintenance costs. Good, so that's a little bit about Minibems. And today's breakfast briefing is about why are most heat networks inefficient? And to talk us through in detail, or certainly with a few ideas, is Alistair Moore. He is part of the business development and sales team here at Minibems. He's a CIBSE certified heat network consultant. I'll be the moderator, sort of just keeping an eye on the dashboard and hopefully making sure things run as smoothly as possible. A little word about the breakfast briefings. We intend to make them regular, so hopefully not too many, but certainly we want to try and keep some kind of constancy to it. It's all about heat networks from design to operation. We will be bringing in partner companies to present their thoughts, and if you're a partner company here listening today, then please get in touch. And we also want to share other webinars that are out there that you might be able to, or you might be interested in. More about that later. So enough from me. Here's Alistair to talk to us about why heat networks are so inefficient. Alistair.
Thank you very much for that, Ben. Good morning, everybody. Obviously, we're trying a new way of working in these crazy times that we find ourselves in. And I just thought it would be a good idea, us at Minibems, where we could maybe keep up our bit of distance learning and our partnership with our customers and our new contacts out there. So really today we're going to talk about heat networks. They can be really efficient if they're basically tackled correctly. However, unfortunately, there's a lot of heat networks out there that are really not that efficient. What we've basically got out there is, I would suggest that the vast majority of heat networks, and I include heat networks as anything that really has a central boiler plant. So anything that's got a central boiler plant, whether it has a heat interface unit or it's direct fed heating system, the vast majority of these are typically over 5 years old. And although we concentrate today on designing effectively new systems, we sometimes forget that these legacy heating systems that are already out there have major problems in them. And as a heat network consultant, I spend a lot of my time looking at these legacy systems because, in truth, if we really are to tackle carbon emissions, most new projects work to the current regulations, and a lot of them work well. They can always work better. But the real issue in terms of poor efficiency is these legacy systems. So what we're trying to look at today is basically the issues that we come up against, and next week concentrate on the solution. So on the next slide, here's a couple of heat network surveys that I did, it seems an age ago. It was only probably a month or so ago. in the West Midlands for a very large housing association that was losing typically £250,000 a quarter between their energy bill for energy generated against the energy that was billed within the flats. And typically, a lot of these apartments had no energy meters, so they couldn't actually measure where this was being lost. So in these two instances, the temperature outside, believe it or not, is -2. And as you can see, the residents' method of temperature control within the flats are to open their windows. And in one instance, in the middle, to open their patio door, it's -2 outside. And essentially, that's their method of temperature control. So that is possibly the #1 cause of inefficiencies. It's really not the design, because the design at the time is to the regulations. The installation typically follows the design. Yes, the commissioning has an impact, but I think the two key things are how these systems are maintained, and the real #1 issue is poor control. So as a heat network consultant, I look at these networks, and I typically give them a rating of freshness between 1 and 100, with 100 being super spot on, fresh, fit for purpose, and 1 being the opposite. And typically, again, I will put an apple or an orange or a tomato against this in various states of rotting, and to show a client how fresh that heat network is, and more importantly, how we can improve it. So a typical issue we have here of poor control is no TRV heads. We have a very inefficient method of radiator control. Unfortunately, some projects will have TRVs, but as we all know in the industry, these should always be presettable. Because if you're running a heat network, the real way of getting your boilers condensing is to basically wring as much energy out of that primary supply as possible, use it within the building, and send back to the boiler plant as low a return temperature as possible. And that is only possible by controlling what happens within each flat and each communal area. And one way of doing that is to use presettable radiator valves. And what they do is basically guarantee you the flow rate through that radiator, irrespective of the TRV head setting. And that enables you to basically get the correct delta T between the flow and return. If you can do that and you can balance the system, then essentially you can make your system very efficient. So on the next slide, the next issue we find is very old control systems. So again, this is the same two projects. So on the left there, we have a panel, and the company that built that panel went bust in the 1990s. And the Schneider Climatronic control at the bottom, I would guess, is an addition from, I don't know, maybe the last 10 years. It gives some element of weather compensation. What the problem it does is it gives you no burner modulation, it gives you no real pump modulation. As long as you want the boilers to come on and off, it works quite well, but it is in no way efficient. And the one in the middle, a Sigma Gear Climatronic system, well, that one really belongs in a museum. So typically what we find is that these projects are running very high flow temperatures all year. And this Climatronic system has some weather compensation, but not much. In fact, the vast majority of projects out there have no weather compensation at all. It is purely boilers on and pumps on peak demand loads on the boilers and pumps, even when there is no peak demand. So on the next slide, another symptom, our pumps set on constant flow. So that little setting on the pump on the left there, with a sail with a straight line through, is constant pressure. Typically, our friendly maintenance contractor will increase the flow rate through the heat network to try and ensure that all the residents have heating and hot water. Unfortunately, the downside of that is that their method of doing it is to open all bypasses, open all valves, open all lock shields on radiators and turn the pumps up to maximum, when in fact an efficient heat network needs to be slowed down. It needs to have quite the opposite. It needs things like top entry, bottom opposite exit on radiators. It needs presettable TRVs. It needs pump sets that will modulate based upon the demand. Unfortunately, the vast majority of systems that I see are set on constant flow rate, constant maximum pressure. And this creates a number of issues throughout the system. On the next slide. The biggest issue that this creates is that you end up with no delta T, no temperature difference between the primary flow and the primary return. This is actually surprisingly good for an old system. I have 10 degrees difference between the primary flow and the primary return. In reality, I saw a project just before Christmas that had 220 flats on it, and it had a 1.8 degree delta T. Basically, what that means is we are sending a lot of energy around the project at high velocity and not using it. And then we're doing exactly the same again. And what you get with that is high thermal losses, high pressure losses, and vast inefficiencies. And the people that effectively pay for this are the building owners, are the housing associations, are the care home providers, and in a lot of instances, the people who actually pay for the energy within the flats, within their kilowatt hour price. And this is a #1 issue in older systems. So to sum up, existing heat network problems basically revolve around this constant temperature, constant flow rate, which gives you a massive oversupply of heat. And basically, there's no real data on how it's performing, other than the central energy bill for the boiler or the CHP or the heat pump. And what that gives you is high aftercare costs, lots of unplanned maintenance, because the maintenance contractor's only route out of this is to turn the boilers up, to make the pumps go faster, and to effectively make that whole heat network completely inefficient. And that's why you see building owners losing $250,000 over a quarter. And that's not a specifically large housing association. It's a company that's big enough, but $250,000 over maybe 40 individual buildings is a lot to lose in one quarter. So let's look at this constant flow rate and constant temperature and what that means. On the next slide. Okay, I quite like this illustration. So if we think of this sushi wheel as a constant flow heat network, and each person on there is an individual flat or outlet, at peak load, when the sushi belt is completely full and all the tables are full, it works exactly as per the design. It does exactly what it says on the tin. The problem comes is when there isn't peak load. So if I remove everybody that's seated from around that sushi belt and leave the lady in the stripy purple top at the bottom and the lady next to her in the red, and remove everyone else, the sushi belt still keeps going around at the same speed with the same amount of food on it. It doesn't adapt, it doesn't flex. And that is really 90% of heat networks out there operate in this kind of manner. And what that gives you is massive inefficiencies, because why send all that volume around when there is no demand? And the reason that really fails is on the next slide, is that what that basically means is that we are supplying 80 degrees to a heat exchanger in this instance. So If you think of this illustration here, the left-hand side of it is the flow and return from the boiler. So the flow's coming in at 80, it's going into a heat exchanger, which basically rubs up two bodies of water across a body of metal and exchanges the heat from one side to the other. So the 80 goes into the exchanger. We're typically getting 75 coming back to the main boiler. On the secondary side, what you have here is the flow rate going into your radiators and the flow rate coming back in. So two separate sides, two separate systems working together. And basically how that works is the temperature gauge on the right, you have demand from your thermostat. It turns the pump on your heating in your HIU. Temperature sensor on the right there basically opens and closes a 2-port valve on the bottom left-hand corner. And you have basically a 2-port zone valve that comes on at the same time. And what that does is it allows the full maximum design flow rate through that heat exchanger. And that is basically irrespective of the load. And basically what that means is that that 2-port valve at the middle, at the bottom left-hand corner, is either open or closed. And the reality of that is that valve is letting through too much flow too often, because it is not matching the real-time demand on the right-hand side. And the consequence of that is that you get very, very high return temperatures. So if you have a CHP unit, we will have all been to site and seen these units, and these units are typically switched off. And they've either been switched off by the building owner because of the maintenance, or more likely, they've been switched off because the return temperature coming back is too high. That also means that your gas boilers won't condensate. Again, that means inefficiency. And purely the maintenance contractor turning the pump speed up makes that worse. It doesn't make it any better. And what it really needs is a whole rethink on how we operate these systems. And that schematic you see in front of you probably accounts for 80% of all heat networks out there that have heat interface units within them. So on this next slide, the reason this system falls down is really quite simple. For constant flow to work, you really need a constant demand. And there isn't a constant demand because the one thing that alters more than anything else in this country is the weather. And unless a system can adapt and flex to suit the real-time demand and the weather, it cannot operate efficiently. So on a day like today, I've got up and gone for a walk very early this morning. It was 2 degrees where I live in the Midlands. It will probably be 10 or 12 degrees at lunchtime, and it will go down to very cold again this evening. And what you need is a system that will adapt to that. And a constant flow, constant pressure system just doesn't work. And the consequence of that is lots of gas and energy usage and poor central plant performance. Now, you really think we should learn by our mistakes on this, but unfortunately, all these old legacy systems pretty much operate the same. So on this next slide that we have, the real consequence of this is that 75% of the fuel is pretty much not delivered within the building. So you have boilers running at full steam. You have pumps running at full, irrespective of the load. And even in the summer months, when you might only have 10% system demand, those boilers and pumps are not modulating. If they do modulate, they modulate very little. So there are rarely summer jockey pumps to reduce the pump loadings in the summer. There are rarely boilers that are set up to drop down to 65 in the summer. And so basically, this means that the energy consumption just gets higher and higher. So the reality of this is that if you are a building owner or a housing association, is that your clients will get heating and hot water. The problem is that the cost of producing it is extremely high. So we have a client here, one particular client, and these are individual sites across their network. And the worst performing heat network is using 52,000 kilowatt hours of gas per flat. Now, most of these flats don't have individual energy meters within them. So these numbers basically come from an energy meter or gas bill at the back of the boiler. And that total is simply divided by the amount of flats that are in that development. So these typical ones here, there are a mix of prepayment, a mix of heat with rent. And we find that heat with rent tends to be the most poorly controlled and maintained system out there, because the only goal is to provide the end tenant with heating and hot water. Unfortunately, that comes down to it has no relevance on the cost of doing that. So we think heat with rent is efficient. It's actually, the opposite. It's very, very inefficient, because there is no incentive for anybody apart from the building owner to try and reduce the energy consumption. The downside of that is that the heat element of the rent may be quite high because of the amount of gas being used on the building. So to take you across from these, the left-hand one, the bottom left-hand one in blue, is a Minibems controlled site with our technology built within an HIU. And that particular project there has full weather compensation. It has demand and supply driven control, so that our job is to purely match that supply and demand. So we're using there under 6,000 kilowatt hours of gas per flat. The next one along is a modern heat interface unit that has prepayment within it, and that is using just under 10,000 kilowatt hours of gas. Now that is a brand new building. The one on the left in blue is an old 1970s concrete brick structure. The rest of the ones to the right are older style buildings again, mostly with heat with rent. So as you can see there, we can bring the energy consumption down quite a lot, and we'll go more into that next week. But one key point to mention there is that we are delivering the same amount of heat within the flat. The kilowatt loading of each radiator isn't any different. What we are doing is essentially wasting less, distributing that. And the key of how we do that we'll cover in a little bit more detail next week. And on the next slide, the real key is dynamic real-time flow control and how this works and how we can basically guarantee these efficiencies on old and new projects, new build projects. And the number one way of doing that is to match supply with real-time demand. It's quite simple really, because what we have at the moment is those two sides of the system don't talk. So on these old legacy projects, what happens in the flat has no bearing of what happens in the main plant room. And that is the real issue, in that the secondary side within the flat does not talk to the primary side within the boiler. And the consequence of that is huge gas bills. And we'll go into that in a little bit more depth next week. And from my point of view, I think that's my final slide. Ben will take you through onto this next section.
Hello, yes, good. So I'm just trying to find out how to unmute myself there. Thanks very much, Alistair. Have we got any, no questions so far? Don't be shy. If you do have any questions you'd like to write to us for us to respond to, great. Well, I did get one from Brian, but that's one for afterwards. Thanks for writing to me, Brian, there. Yes, if you've got any questions, let me know. Write them down there, or of course you can get in touch with us afterwards. We're sort of coming up for our sort of our target, and was to sort of finish around 9 o'clock, subject to any other questions. But yeah, just to let you guys know that there's a couple other webinars this week. One today, being held by Giacomini, and Giacomini are one of our partners. In fact, they have Minibems hardware embedded in their heat interface unit to the G6, and yeah, that means that when the G6 heat interface unit is fitted, you sort of just need to switch it on and you can get all these great Minibems services. Chris Doherty's the man to get in touch with there if you'd like to subscribe to that webinar, or indeed any of them, because they've got a whole range of lunchtime seminars programmed this week and next week, and quite possibly into the future as well. Also, there's a company that we partner with called Hysopt. Got a very interesting technology that was actually an award-winning software. So it won the CIBSE award for most innovative software this year. What they do is they run a software that can optimize a heat network at the point of design. And the man here in the UK that you should get in touch with about that is Chris Davis. So the details up there. If you need any other details, feel free to get in touch with me. Yeah, and that's basically it. Please get in touch with Alistair if you've got any projects you'd like to discuss. There are his details. If you want to talk about webinars or other co-marketing opportunities, please feel free to call me or get in touch. We will be repeating this webinar again live on Thursday, same time. So if you would like to recommend it to any of your friends or colleagues, then that would be great. I would appreciate that. And stay tuned. We will let you know the timing for next week's webinars when we are going to discuss how to achieve dynamic real-time flow control.
Thank you very much for your time, everybody. It's been a pleasure. And for our first one, thanks for bearing with us with the odd little hiccup, but I think we'll get there.
Thanks very much. Cheerio.
Thank you. Bye-bye.